Most AI integrations begin as bespoke API wrappers, single-purpose bridges connecting one model to one tool. As connections grow, these bridges inevitably buckle. To connect N different AI models to M internal tools, an organization must build and maintain N times M distinct integrations. Wiring 5 AI applications to 5 internal databases requires 25 custom pathways. Each one carries its own authentication logic, unique error handling requirements, and a permanent maintenance burden. This architectural friction persists when engineers solve protocol-level bottlenecks as if they were a series of isolated plumbing tasks. Without a standardized layer for context exchange, the infrastructure required to support these models becomes too heavy to scale. The Model Context Protocol, or MCP, replaces that chaotic web with a universal interface, shifting the integration requirement from N times M to N plus M. While Anthropic introduced the protocol, it is now a vendor-neutral standard governed by the Linux Foundation, supported across major AI ecosystems. This is Bridging Tech in Concrete. Today, we are analyzing the technical architecture of the Model Context Protocol. By building an MCP server for a data source once, any MCP-compatible client, from Claude Desktop to custom agentic frameworks, can interface with it immediately. This allows developers to stop writing repetitive connector code and start building the core functionality of the AI tools themselves. The MCP architecture defines 3 specific roles: the host, the client, and the server. The host is the user-facing application coordinating the interaction. Within it, a dedicated client manages communication with a precise one-to-one mapping. The server is an isolated program providing external context, acting as a secure buffer to retrieve data without exposing systems directly to the AI. Because these components are modular, a single host can coordinate several clients at once to complete a multi-step task. The data moving across these boundaries is formatted as standard JSON RPC 2.0 payloads. This approach removes the need to hard-code tool documentation or retrieval logic directly into an LLM system prompt. MCP manages the exchange of context only. It does not control how the model reasons about that context. By strictly separating these concerns, a failure in an external tool remains isolated, preventing it from crashing the entire host application. The protocol functions in 2 layers, an inner data layer that defines the message content and an outer transport layer that defines the delivery channel. MCP utilizes 2 primary transport mechanisms, beginning with STDIO, standard input and output. STDO is the default for local servers. It provides a secure, direct pipe to a single client running on the same machine. The second mechanism is streamable HTTP. Remote servers use it to handle multiple clients across network boundaries, providing the stability required for production environments. These transports create a controlled security boundary, allowing hosts to manage authorization and session isolation before any data reaches the model. Because the transport layer abstracts the delivery details, the JSON RPC data remains identical, whether the tool is running locally or in a remote cloud VPC. A server exposes its capabilities through 3 distinct primitives: tools, resources, and prompts. Tools are active capabilities. They allow the AI to trigger side effects, such as running a calculation or executing a database query. Every tool includes a JSON schema. This schema provides the mathematical definition of the input parameters. Resources are passive, read-only data sources, retrieved via specific URIs. They provide static context, like the contents of a log file or a reference document. Prompts are instructional templates that share domain-specific best practices for a given service. These serve as an instruction manual for the AI. Packaging prompts with tools ensures the model understands exactly how the server creator intended the capabilities to be used. The lifecycle begins with a protocol handshake, where the client and server negotiate which capabilities they both support. In the discovery phase, the host fetches all available tools from every connected server. The host then aggregates these into a unified tool registry that the language model can see. When a user makes a request, the model evaluates its goal against those registered schemas to decide which tool to invoke. The host intercepts that decision and routes the call to the specific MCP server that owns that tool. The server executes the task and returns a structured response payload. This result is fed back to the model, which integrates the information into the natural language conversation. This dynamic routing removes the burden of API management from the model, letting the AI focus entirely on reasoning about the data it receives. Because MCP standardizes how AI accesses data, it is often mistaken for a replacement for traditional REST or GraphQL APIs. Traditional APIs provide fixed, predictable endpoints designed for software-to-software integration. MCP acts as a translation layer that sits on top of existing APIs. It turns the rigid structure of a standard endpoint into an adaptive interface for an AI model. This enables the model to discover and use tools at runtime, which is a significant departure from the hard-coded endpoints used in traditional software. It also provides a critical governance layer. The host manages access and session isolation, limiting the model's autonomous reach within the underlying API. MCP does not replace the API. It provides the structural framework an AI model needs to orchestrate the APIs you already have. Adopting a unified standard like MCP allows agentic systems to move from isolated prototypes into production environments. Let us know in the comments, what legacy tool or database is your team currently struggling to connect to your AI workflows? In Part 2, we will open the terminal and build a functional MCP server from scratch. A stable AI system requires a foundational protocol that is as rigorous as the models it serves.